eat all y'all at lunch. So I won't try and belabor this too much. So yeah, I'm going to talk about what happens with the impact of amorphous water ice and primordial icy bodies. You may notice this doesn't sound like it has anything to do with spectroscopy. It doesn't. This is American law. So let's start off with what is amorphous water ice. So we're used to crystalline water ice. This is hexagonal ice, or ice 1H, which is what we're used to down here. Maybe not in Taiwan, but where I'm from in Michigan, where it's cold. And so we're used to sort of this crystalline structure, and it freezes, and you slip on it, and it's all great. But there's this other form that ice can take where it doesn't have a crystalline structure. It's condensed out, and it doesn't have a regular pattern. It's glassy. It looks like a glassy water ice. This is amorphous water ice. And it is inherently metastable. It would like to transition to crystalline ice, but it didn't quite get there. So why am I talking about amorphous water ice? That's because the conditions in the protoplanetary disks, especially the protosolar disk, are thought to favor the formation of this compound. And the way it works is that if water is being condensed out and it's trying to diffuse to a lattice site in the crystalline matrix, but you're able to condense the next layer faster than you can diffuse to the lattice site, you can get trapped in the wrong place, so to speak, and you end up laying down an amorphous water ice deposit instead of a crystalline water ice. So if the water flux is high enough, you can do this. Now this is temperature dependent because this is a diffusive process. And so it's fast and it's wiggling more, and you can find the lattice sites more easily. So it's a temperature dependent process. And so from Chesla et al., or Chesla 2014, and plotted this out, where if you have a function of temperature and water flux, these are the critical minimum fluxes required to condense amorphous water ice instead of cubic crystalline ice, or, sorry, one of these is supposed to be hexagonal. Let me go to the next bit. There we go. So for in this sort of region, we'll form amorphous water ice, or AWI for the rest of this talk, instead of the hexagonal water ice. Ice 1 can also take a cubic crystalline form, and so we have this region as well. And if we can compare this to solar nebula H2O condensation models, we can find that there are regions in these models where they are well within this color region. And so if we're in this region, conditions for amorphous water ice formation can happen in solar nebula. All right, so where does this happen? Cold midplane, comet forming region. We've seen a lot of these forms. Honestly, we'll have a better form for this image, but we'll go with this one. Now, this comet forming region is not just water, it's a whole bunch of other schmutz that we talked about. And so when this amorphous water ice gets in place, you can have various other things trapped in it. Here we have a CO molecule, here's methane, but it can trap things. So why is this important? Well, as we talked about, amorphous water ice is metastable. It would prefer to crystallize. It wants to liberate that energy when it diffuses to a lattice site. And so for pure amorphous water ice, when it crystallizes, it can release a significant amount of energy, a lot of heat. Conversely, if it is impure, if it has these trapped species in significant quantities, really like just a few percent, which is pretty modest, then it actually saps all this energy out and can become more or less energy independent, or even require a little bit of energy to come out. But the bottom line, though, is that as amorphous water ice crystallizes, it can either release heat or it can release trapped volatils, which makes this a very promising avenue historically for exploring cometary activity. This crystallization timescale is temperature dependent, so we're looking at timescales on the order of seconds. I'm a theorist. So we're going to say the next time units in temperature over here. We see that this is clearly temperature dependent because as the molecules warm up, they wiggle more, they can find those lattice sites, and so they can crystallize much more quickly. Now we often hear things about amorphous water ice, like it crystallizes at 120 or 140 Kelvin, but that's just because that's what we can measure in a laboratory. It happens fast enough for us to see it, but if you're below about 80 Kelvin, you're stable over the age of the solar system. So we think that if amorphous water ice can survive and get placed into the reservoirs, it can survive to the present day. And so because of this, amorphous water ice has been proposed to drive activity, distance, and icy bodies either held up at 25 plus AU, or Echeclus, the Centaur 13 AU, which had a massive event. And it's also been proposed to drive activity much closer in, even in JFCs, such as this outburst in the Imhotep region of 67 Pete, Churyumov, Garrison, Mako. At 3.3 AUs, been proposed to require internal energy sources, or on 29 P Schwarzman-Bachmann 1. It's thought that it can also explain this activity because if we look at the size of SLA1, which is about 30 kilometers, you compare that to this AWI depletion time calculated in Liss et al. 2022, what you find is that the time scale required to get rid of the amorphous water ice is longer than it would take for this object to migrate to where we see it, and so it's thought that this could explain the activity of 29 P Schwarzman-Bachmann 1. But it should be noted that all of these ideas more or less assume that this primordial amorphous water ice can survive to the present day. Now, I'm using the term primordial amorphous water ice to differentiate the amorphous water ice from the formation of the solar system, as opposed to later forms of amorphous water ice that can form from cosmic ray exposure, usually in the surfaces of these bodies that we're talking about, just AWI all the way down. But all these assume that we can get this amorphous water ice out of the reservoirs without destroying it. And there's a big question about this. What about planet migration? So, I'm not going to call this an East model, so I don't want to make the dynamicists explode. But let's talk about planet migration, where we have this early prototype belt, the planets destabilize it, and everything gets scattered out. But this is a highly, highly violent process. And so we would expect that there's a lot of collisional grinding, collisional processing during planet migration that actually place these things in the reservoirs. And so this begs the question, can amorphous water ice even survive the shock heating of these impacts? And that's what we wanted to look at. And so we look at impact speeds during planet migration, which are much faster than today, a few kilometers per second, whereas in the reservoirs today, they're just a few hundred meters per second, if that. And so what we did was use ASIAA, the ASIAA shock physics code to simulate impacts between icy bodies, and then at various impact speeds, and using solid bodies, and we'll move these play. Or is this going to break the computer? It broke the computer. All right. Well, there's a really cool movie. Since they didn't play, they're the best thing you would have ever seen. I kind of went a little bit. Okay. What we see is that you got these slow impacts, you got faster impacts, and these are they just completely destroy each other. What we want to know with ASIAA is that we can take every part of that simulation, place what's called a tracer particle into it. It just records conditions. In our case, we care about the temperature. And so we can say that, like, what was the temperature profile of the material that started in this red box? We're in these other places. We can see what the temperature they felt throughout the impact simulation, and then we can run this through a crystallization script that uses that amorphous water ice crystallization timescale. And when we put all of this together, it lets us calculate during this impact process how much of the initial amorphous water ice that may have been present in any of these parts of the body, how much of that could have survived the impact process. And so, how much can survive? Well, actually here I'm plotting how much doesn't survive. This is how much crystallizes. Near the impact site, 100% crystallizes, which is not surprising in this particular simulation. And further out, more can survive, where there's less shock heating. And so what we find is that the survival of amorphous water ice is highly sensitive to impact speed. So on the left, I'm plotting how much amorphous water ice is completely unaltered. And by that, we define it as just less than 0.1% crystallized. So nearly all the amorphous water ice that was there would still be there, versus destroyed AWI is 1 minus that. It's how much is completely lost, greater than 99.9% crystallized. And so there's this very sensitive trend right around a few kilometers per second where we go from nearly all of the amorphous water ice surviving to nearly all of it being destroyed. And so at the current impact speeds in the reservoirs of just a few hundred meters per second, amorphous water ice can survive no problem. But during planet migration, a few kilometers per second, this amorphous water ice can be lost very quickly. Now what we see is that during a single impact, you may only lose half or a few tens of percent, or at the very least you would expect some to survive, but over subsequent impacts you may lose more and more and more of this. I should point out we also looked at other properties. This is part of a sensitivity study. We looked at initial temperature, absolute size of the bodies, relative size of the bodies, What we found in this particular study was that only the impact speed seemed to make any significant difference. But there was a major simplification that we made that may cause some significant problems. We assumed that all of these bodies had zero porosity, largely to make the computations more tangible initially. And there's really two kinds of porosity that we can talk about: macro porosity, which is space between the grains; micro porosity, which is space within the grains. But at the end of the day, we don't really care which one it is, because either way, we just care about how much material is there and how much void space is present. The reason that porosity is important is that crushing out pore space saps a lot of energy. You have to take these grains, deform them, rub them against each other. It takes a lot of energy to crush out this pore space. And by releasing this energy locally, we create significant local heating. And so what we wanted to do then is just explore how much porosity can affect this process. So all of these simulations are 100-kilometer bodies striking each other at 3 kilometers per second, and they differ only in their porosity. So we try anything from 0 to 75% porous. And the first thing we can look at is how the peak heating. There we go. So one thing we can look at is the peak heating experienced throughout these bodies and how it varies as a function of porosity. And what we find is that as we get more and more porous, all other things held equal, we find that our peak temperatures rise incredibly quickly with increasing porosity. I just like to point out the top of the scale is 300 Kelvin. It's above the triple point of water. There is no way amorphous water ice would survive that. So we can do the same thing we did before, take those tracer particles, run them through the crystallization script, and we can calculate how much amorphous water ice survives. And what we see is that when we go to higher porosities, we lose more and more amorphous water ice. And so what this tells us is that porosity can significantly impact the destruction of amorphous water ice, primordial amorphous water ice, and therefore we really need to consider how porosity can affect these processes. And indeed, we find that it's actually very rapid. Whereas we see that we lose our amorphous water ice in these particular simulations at around 40 or 50%. I should point out that comets like 67 Petrie along Mako is measured to have a porosity close to 75%. These things are just empty. We also looked at just keeping that 75% porosity, which is very comet-like, and we just varied the speed a couple of cases as the money ran out on the grant. And so we only had a couple of points here. What we can see is that at slow speeds we can survive, and then as we get faster and faster, it's all gone. So the trend is still there. So what this tells us is that the survival of primordial water ice to the present day is an incredibly strong function of an object's porosity and its particular collisional history. So what can we do with it? Well, we can look at the protoplanetary disk during planet migration, and we can see that impact speeds in the inner disk were much higher than in the outer disk. And this can lead to differences in the amount of material that ends up in each reservoir, or how much amorphous water ice is present in each reservoir. By this I mean if the two comet reservoirs, the TNOs versus the Oort cloud, have different collisional histories, and we can expect, I'm sorry, I'm getting ahead of myself. Let me go to the next slide. So what this suggests is that if these objects have different collisional histories, then there may be a significant and measurable difference in the amount of amorphous water ice that can be found in these populations. And so this is something we really want to explore next and try and see if we can actually take these models and actually run them through the collisional histories that have been measured, or at least calculated, and we can try and get an estimate of how much of this amorphous water ice can survive to the present day in each population, and at the very least as a function of porosity. So to summarize, we find that amorphous water ice is highly sensitive to impact speed and to porosity, and that potentially differences in collisional histories can give us significant differences in the amount that survives to the present day.
Questions? Yeah, can ISAIAA assess the compression in these collisions?
I'm sorry?
Can ISAIL assess the amount of compression in the collisions?
In terms of how much they compact.
Yeah.
Yes, I'd have to get back. Oh, I don't want to make a claim on that. I think so. I'm pretty sure it does. I'd have to get back to Brandon Johnson on that.
Hi, Joshua Barkowski, Utah. I thought this was a really cool talk, and I'm just wondering, when you talked about like sort of getting to see the difference in the amount of amorphous water ice, is there a way to like observe that and then basically be able to say maybe where something's come from?
So let me skip ahead to just sort of this backup slide that I have that actually kind of helps with this. The problem is, and this is actually something originally discovered by Simon Porter, who's in this room, I believe, somewhere. Say hi, Simon. There you are. 2010, he had a paper looking at micro impacts of striking these bodies. And there's so many of these micrometeorite impacts that it would effectively do the same process, right? So if you're just being bombarded with impacts, you'd expect that anything we look at, even if it's got an amorphous water ice-rich interior, even if that were the case, I wouldn't necessarily expect us to be able to observe anything, so I would expect there to be pretty much a crystalline ice mantle on top of it. So I don't know how easy it would be to do observationally. I also know that detecting a 1.65 micron feature and interpreting it, from what I hear, can be a real bear, but that's the closest I'm going to get to spectroscopy.
Hi, I'm Aaron from UBC. You said there are microporosity and microporosity. How do you measure microporosity?
How do you measure microporosity? That's a good question. The short answer is I haven't been involved in the spacecraft, but I believe it was done. I think Rosetta was able to measure this, and someone correct me if I'm wrong, using, they had an instrument that could actually see dust grains and collect them and actually look at them. And so one way to measure microporosity is just look at these things under a microscope and be like, hey, look, it's very fluffy. And that's one way they did it.
Yeah, they also did radar sampling.
No, there you go, thanks, Simon. Radar sampling can do it too, yeah.
So how did you model that?
Sorry, how did I model which part?
The porosity.
It's the bulk. So we're measuring the bulk porosity. It's a parameter that we can specify in ISAIL. It's just like we can specify impact speed.
It can be technical. I understand.
So we just specify. So what we do is we actually specify we specify a property that's akin to porosity. It's the dilatancy, right? How much is the material expanded versus if it were just zero porous, which is equivalent to porosity. So we specify that as an input, so we can actually tell you what we actually know what the initial porosity was in each of these simulations.
What did you do with the remnants of your collision?
We just let them stay as rubble. It didn't really matter. Because what we wanted to know is, so we assume that these materials just break up and they're destroyed. These are catastrophic disruptions. So every one of these will just break them up entirely. We wanted to know, and then presumably these things can collide and reform into smaller bodies. We think that a lot of the comets, JFCs that we see are collisional fragments of larger bodies. And so what we're looking at is what happens to the material that would form those collisional fragments. So we don't directly address what happens to the ejecta. We don't address how it reforms. We just want to look at the faces of the ices that are scattered back out into space during these collisions.
I want to know what happens if you have other volatiles as well. So we're seeing a lot of CO2, maybe less CO. So I'm wondering is what happens when you also have that? Is it possible that you start triggering more significant activity but then totally destroys your amorphous water?
Yeah, so potentially, that's a really good question. Potentially, yes, we can destroy them. So let's just imagine we have a big chunk of material that's thrown off as a fragment. Let's say we just spit off a 1 kilometer object that later becomes back. There could have been CO2 in there, there could have been amorphous water ice in there. When the shock wave passes through, we don't necessarily lose any of the water. We just change it from amorphous to crystalline, so everything is still there. The CO2 that was present, it may briefly shock heat, but it can immediately, these are incredibly short pulses of heat. So they don't really have time to go anywhere. They just get hot and then they cool off again. but it's enough to destroy the structure of amorphous water ice.
Let's thank our speaker again.